Next, we're going to discuss the fact that horizontal and vertical motion are independent. And conceptually, this idea is really a big deal, and it applies in a lot of situations. Whenever you have motion in two dimensions, you can think about the horizontal motion, and you can think about the vertical motion, and you can and should think about those two motions independently. So let's think again about the boat crossing the river. Okay, here's the river banks, and our river's flowing here. And here's our boat, and it's aiming across the river like this. And again, we can think in terms of north, south, east, and west. So when we say vertical motion, in this case we're talking about motion along a north-south line. And when we say horizontal motion, we're talking about motion along an east-west line in this particular case. So the boat heads south. That means that its velocity is a vector that points to the south. So relative to the water, the boat is moving along a line that runs north-south. And the current in the river is to the east. We'll draw an arrow representing the current. The current is to the east, so the velocity vector for the current is this arrow that's along a line that runs east-west. The speed of the current will affect how far downstream the boat lands. So instead of coming straight across, it gets dragged downstream, and it lands somewhere downstream of this point directly across that it was aiming at originally. It ends up getting carried downstream by the current. And how fast the water is flowing affects how far downstream it ends up. But the key idea to understand is that this horizontal motion, carrying the boat downstream, has no effect on the vertical motion, the motion of the boat across the stream. Those two things, the vertical motion, in this case north-south motion, is completely independent of the horizontal motion, what we're calling in this case the east-west motion. So the time it takes the boat to get across depends on how fast the boat is moving. That's that vector right there, the velocity of the boat, and on the distance it is from one side to the other. And those things have no relation to the horizontal motion of the river, or the fact that the boat gets carried downstream. In other words, the motion of the water doesn't make the boat take any longer to get across the stream. Now, if the boat were aiming upstream, if it were traveling against the current, then certainly that would slow it down, and any trip it were trying to take in that direction would take longer. And if the boat were going with the current, then the current would be helping push it along, and any trip it were taking in that direction would take less time. But if the boat's going perpendicular to the direction of the current, like we have here, then the time it takes to get across isn't affected by the speed of the river. Okay, let's actually do the math for one of these. Suppose the stream is 80 meters across, and the boat is traveling at 10 meters per second. How long will it take to cross the stream? Well, you can probably do this in your head. If it's going to go 80 meters at 10 meters per second, then you can probably tell that it will take 8 seconds, and that's the correct answer. Or if you want to, you can do the math. And here it is. You should understand that time will be distance divided by the velocity. And the distance in this case is 80 meters, and the velocity is 10 meters per second. And you can see meters cancel, and 80 over 10 is just 8, and we're left with seconds right there, 8 seconds. So that's what we said earlier. So you can use the equation, or if you can do it in your head, you can do it in your head. So it takes 8 seconds to cross the stream. Now what I'm saying is that that is the time it will take regardless of the east-west current. So the boat leaves this side of the stream, and it's going to travel this distance, 80 meters. And it's moving, here's the velocity, it's moving at 10 meters per second. Now, if the water is still, the boat's just going to go straight across like this and land there. If the river is flowing east just a little bit, it's going to drift to the right a little bit. And if the river is flowing east very quickly, it's going to drift to the right a lot and land right there. If the river is flowing to the west a little bit, then as it crosses the stream, it will get pulled downstream, which will be to the west in this case, and it will land there. And if the river's flowing to the west very fast, it will get pulled downstream and land over there. In any of those cases, it will still cross the stream in 8 seconds. The vertical motion is described by this 10 meters per second and this 80 meters. It goes this speed for this distance. Therefore, this math applies, and it ends up taking 8 seconds. The horizontal motion of the river, whether the river is flowing to the right or to the left, whether it's flowing fast or slow, or whether it's flowing at all, doesn't affect the time that it takes to cross the river. In other words, the north-south motion across the stream is independent from the east-west motion upstream or downstream, the flow of the current. The horizontal and the vertical motion are independent. And that fundamental idea that the horizontal and vertical can and should be treated separately applies to a broad range of situations, not just boats on rivers. And we'll see some other cases as well.